All right, now let's show some of the power of having thermodynamic data about a reaction. We have thermodynamic data here for the dissolving of lead 2 chloride, and a word or two about the fact that there's a double arrow here. Typically in thermodynamics, you're always talking about the forward reaction, and so I've used a forward arrow only in almost all of the lecture videos for this topic. However, based on equilibrium, we know reactions go both ways, so it's also okay from any time after equilibrium through the rest of the course to use a double arrow. We know all reactions go both ways to some extent, or in theory anyway. So anyway, that's why we've been using a single arrow, and we're going to actually, as part of this example, show the reaction possibly going both ways or either way, well, different amounts of reaction before we get to equilibrium. So we've got the double arrow back in. Now the question itself says calculate the solubility of lead 2 chloride as a function of temperature at 25 and 50 degrees Celsius using only thermodynamic data. Okay, so we have all of our thermodynamic data. Please pause the video and go ahead and write it down. I'll wait. Good. Now, now that you've got all your data written down, we will start by calculating delta H reaction, naught for standard conditions. Same thing for all three of them. Delta H reaction naught. Now remember to include the 2 here, and so I might just write this 2 in here so I don't forget. So it's going to be 0.92 minus 2 times 167.1. It's really a plus, but I went ahead and put the minus 1 in there anyway. And now it's minus reactants, a double negative, so plus 359.4, 26.1 kilojoules per mole. Endothermic tends to be non-spontaneous. Delta S naught reaction. Well, we're going to aqueous species from a solid. Let's see how this turns out. 18.5 plus 2. Whoops, let's try that again. 18.5 plus 2 times 56.6. 131. Wow. Minus 4.3 joules per mole Kelvin. That's a bit surprising. Probably has something to do with this low number for the lead ions. Let's go with it. And then delta G, so 24.4, which is negative. Add a negative number, so minus 2 times 131.2 minus 238, I think I did that right, plus 314.1. It's really a negative of a negative, that's why I did a plus. Delta G reaction equals, something's up here. 131, 260, 270, 280. Let's do that math again. So 24.4 negative. Oh, that's it. Maybe minus. Minus 131.2 times 2. There we go. Plus 314.1. There we go. 27.3 kilojoules per mole. Non-spontaneous. If you remember way back, we talked about the solubility of lead chloride, and we declared it insoluble. It turns out it's only very slightly soluble. Let's solve for that now. So we're at 298. So that's 25 degrees Celsius. So we're at standard conditions as far as temperature goes. That means that we can use delta G naught reaction equals minus RT ln K. And to get the equilibrium constant, the equilibrium constant is going to be a Kc because we have concentrations of our aqueous species. There are no gases in here. The solid is not in any equilibrium constant, so we can have a solid as well. All right, and so we want to get Kc by itself. We found that Kc equals E to the minus delta G over RT. That's minus 27,300. Oh, there's my E term. R 8.314. And so we have, well, the units do cancel. Here's 298 Kelvin. Calculating all that out, so 27,300 minus divided by 8.314 divided by 298 minus 11. Now we take the exponential. 1.64 times 10 to the minus fifth. So Kc equals 1.64 times 10 to the minus fifth. Now it asks the solubility. That's going to be using a dissolving reaction, how much lead 2 chloride dissolves. Uh-oh, we've hit the time of day where the sun's finally coming in. Let's power through this, at least this one. If you want to know how much reaction occurs, you need an ice table. This one's going to be in terms of molarity. And don't worry, we're setting up the ice table, but we have plenty of space on the next pages to solve it. Take your solid. Write out your reaction. Kc equals 1.64 times 10 to the minus fifth. And now we have a solid in our ice table. Solids don't show up in equilibrium constant expressions, so we can neglect it. We have 0 here and 0 of our products to start with. We have plus x because we're going to be assuming that only a tiny bit is dissolving. We have plus 2x here, and our equilibrium amounts are right there. Now, we'll write out our equilibrium constant expression. For our equilibrium constant, it's going to be concentration of lead 2 ions times concentration of chloride ions squared equals x 2x squared, and it equals 1.64 times 10 to the minus fifth. We can simplify this portion right here into 2 squared as 4x squared times x is 4x cubed equals 1.64 times 10 to the minus fifth. Divide this by 4. And then take the cube root. How do I do that on my calculator? Let's do, there we go, shift. I don't know if that's going to do it. Cube root, there it is. Shift cube. I get 0.016 molarity, and that means that that will be the concentration of my lead ions. 2x will be the concentration of my chloride ions. And so I'll multiply this times 2. And that is, well, technically this first one, which is X, is the solubility. But those are the concentrations of the ions at 25 degrees Celsius. Now, let me reconfigure here for a second. There we go. Get out of the sun a little bit. A little bit anyway. All right. And I got out of my camera too. There we go. Always making readjustments on the fly. Now, on my third page, let's do this at another temperature. In order to do anything at another temperature, we need to take our delta H and our delta S and calculate delta G at the new temperature. So this is going to be 50 degrees Celsius. We're going to need delta G equals delta H minus T delta S. Then we know that our new temperature is going to be 50 degrees Celsius, which is 323 Kelvin. So plugging everything in, let's see, we've got 26.1 kilojoules, so 26,100 joules per mole. T is 323 Kelvin. And here we have minus 4.3 joules per mole Kelvin. Multiply that out. I get 27,488.9 joules per mole. So, and we'll round that to 3 sig figs, although that's very close to what we had before. Let's change tactics. Instead of 50 degrees, let's do another one. Let's do 200 degrees Celsius. No, that doesn't even make any sense because we won't have any water anymore. Let's do, well, let's just stop while we're ahead. We can see that the delta G is very close. Oh, yeah, that's right. And therefore, we can see that the solubility will not change much. For this reaction, because it's such a weak function of temperature, there is not much change in the entropy.